Hi all. So in today's video, we're going to look at discrete moments. So if you recall what a moment is, it's when we just put a function into the expected value. So in other words, let's kind of look at the expected value and see kind of what happens here. So the expected value, if you recall kind of what we had here, we just have this function, right? So there's not too big of a difference. Like the expected value, nothing really changes, right? So here's like the expected value, and it's something to kind of keep a note and something that works. But there is one caveat here, right? This might be an infinite sum. So we need to make sure that the sum is well defined. So we need to make sure that the sum is well defined. So this is only true, at least for us, when the series is absolutely convergent. So in other words, what we're saying is this can't be equal to infinity, right? That's what we mean by not well defined. So what we say is we say that the expected value e of x, as defined above. Oh, we say that it is e of x. Sorry, I was confused about the notes. So the expected value is e of x if, so this is the big things, if the series is absolutely convergent. And what does this mean? If you don't remember off the top of your head, what this means is that this summation converges. Converges, if you remember. So here, let me grab bananas. So it converges means that this is less than infinity. The absolute part is basically coming from the absolute value here, right? And so one might ask, well, why do we care about absolute convergence and not normal convergence? Like, why can't we just say, well, just have it just normally converge? Who cares, right? Like, what's the difference? So this is actually coming from the Riemann series theorem. So if you're not used to this, this might be something that you might want to quickly look up just to remind yourself what this is. And basically what this is saying is that I can, if it absolutely converges, I can take my summation and I can rearrange my components, my summation parts, and I still get the same sum. Now this is not always the case, right? Like there's well-known examples of things that fail this, where you can be convergent but not absolutely convergent, which basically means I can now rearrange my numbers to get any number I want, which is kind of weird. And that summation will always be finite. A good example of where this kind of fails is like when people do this summation as a joke, where they do 1 plus 2 plus 3 plus 4 plus all the way up to infinity is equal to minus 1/12, right? So this is a standard example of where you need absolute convergence or else you get problems. You can't just shift things around. So obviously, if you're used to this, you know that this is not true. But yeah. So notice that all of our discrete distributions are convergent if and only if they are absolutely convergent. And this is because we always have that our probability is always greater than or equal to 0. And we stated that our sample size is all non-negative integers, right? So this part is basically guaranteeing that if we have convergence, then we have absolute convergence. So we don't really need to care about absolute convergence unless we're allowing negative terms into our sample space. And that does happen sometimes due to like equations we add or something. But just note that for us, usually it's just something you should keep in the back of your head. So now let's look at some moments. Like, what is a moment, right? So remember that a moment for us is basically when we take our function, our expected value, and we add some term in it, right? X squared or x cubed, etc. But we can do this with any function, and basically the function that we get is the following, right? So we have this function here. And basically this is defined if the right hand side is absolutely convergent. And this is why we're saying that, why I'm making this absolute convergence thing, because it's very easy to note that this f of x, wait, this is, I wrote this wrong. This should be little f. This should be x here, and this should be little x here. And so what you'll notice is, let me write, so we need to make sure this is absolutely convergent. So we'll stop here for this video, and we'll look at an example of this in the next, like this discrete moment stuff, in the next video of kind of how to handle this absolute convergence and how to handle adding functions and all of that. So I will see you then.